Hi, so in this video we'll see how you can create the layout of a simple inverter. I'm using my VirtualBox setup here. So once I open the terminal, go to my workcad directory. You enter C shell, source the cadence.chsrc file, hit IC to start up Virtuoso. So once Virtuoso comes up, of course I go to my library, which is test underscore 65 nanometer. In this I go to my cell that's called inverter underscore 65 underscore layout. Here I have kept a schematic of a inverter ready. So this is a simple inverter that is minimum sized. So the length of both the NMOS and PMOS transistor is minimum, which is 60 nanometer, and the width of NMOS transistor is 80 nanometer, and that of PMOS is double of that, which is 160 nanometer. Now let us see how we can create a layout for this schematic. To do this, first of all go to launch, select a layout Excel, read this and click OK. The details on this window are also OK, so I click OK. We wait for the layout editor to come up. So once this is up, you see that it places both these windows side by side, which makes it convenient for you to refer back if required. So let's go to schematic editor, hit F so that we can see the whole design at one time, the whole design together. In the layout editor, of course, let's now create the instances. To do this, go to connectivity, select generate, then select all from source. Here we are only interested in generating the instances, so let's deselect IO pins and deselect PR boundary. Then let's hit OK. You see that it's created an instantiation for PMOS and an NMOS transistor. However, this doesn't look anything like the transistors we saw in the previous video. So what we'll do is hit Shift and F. This displays the layout inside an instantiation. So those red empty boxes are now filled up with the content of those boxes. Of course, everything I'm saying in this video is been documented, as I always do. So if you open the browser, you can find all documentation at the usual place. So if let's go to a lab website, which all of you know is chips.ec.iisc.ernet.in. Then go to the courses page. There select the current course, go to the lab instructions page. From there we will scroll down and go to the first lab instructions page, and then we come to the instructions about layout setup. So by clicking that, we come here. Before the layout setup can be started, some initial steps have to be performed to ensure that you copy the relevant files into the correct directory. In your case, the working directory. For people who use VirtualBox, few additional steps are required, all of which has been detailed clearly here. So all you have to do is go to this website and copy paste these commands. You will require the root password of your VirtualBox, which I will give to you in the class. So everything I'm telling, like I mentioned before, is listed on this website. So everything from launch, the layout editor, and what I'm going to say from here on forward, I will update these numbers. Some of them are not correct at this point in time. So all of this is here, so you don't have to spend any effort in trying to make notes in class. So let's get back to our layout editor. You saw there's a PMOS on top and NMOS on bottom. If you see the schematic, when I select the PMOS layout in the layout editor, the corresponding transistor in schematic editor highlights. Likewise, when I select the NMOS transistor here, the NMOS transistor highlights. So that can be really helpful. In when you're doing layouts of bigger designs, when things get complicated and it's hard to make out what represents what. So first of all, let's draw the power rails for VDD and ground. The way that you draw anything, let's start off by drawing rectangles. To draw a rectangle, the shortcut is R, so hit R, select the start point and click at the start point and click at the destination point, so you have a rectangle. If you want to undo any action that you previously did, just hit U, just as you did in the schematic editor. The palette on the left here shows all the different layers that are there. So we want to draw the power rails in metal 1. So let's scroll down and select the metal 1 line. So let's scroll down, and this line called ME1 refers to metal 1. So to draw this, we want the metal line to run above PMOS, so let's go there. The way you zoom here is use the right click to zoom, just like you did in the schematic editor, and when you want to zoom out, hit Shift Z. Okay, let's draw a rectangle by hitting R, start point, destination point. Now we need to set the display properties. To do that, first go to options, then go to display. For minus spacing, the minus spacing allowed by our foundry is 5 nanometers, so and all the numbers here are in micron, so let's type 0.005. Major spacing will keep around 10 times that one, so let's keep 0.5. X minus spacing 0.005, y spacing 0.005. So once that is set, hit OK. So once that is done, let's come back to our layout. I zoom here to see how big a rectangle I have drawn. So I roughly want to know roughly know that I want to draw a metal line of width 0.2 micron, and the way you measure stuff on the layout is by using a ruler. You bring up the ruler by hitting the letter K, the key K. So let's K from start point, end point, and we see that my width of my metal line happens to be exactly 0.2 micron. So that is done. Let's hit F to fit screen, just like we did in the schematic editor. We need one metal line at the bottom that is necessary for the ground line, so let's copy this by hitting C. Select the okay, you see by mistake I have selected the NMOS device, so all the actions I do correspond to NMOS device. So let me hit escape and click elsewhere so that NMOS becomes deselected. You see that highlighted white box is now gone. Let's move the NMOS device up. So to move anything, hit M, click that and move. You observe that whenever I move things around in layout editor, they only move either in the X direction or in the Y direction. This actually can be very helpful when you're doing complicated layouts. We'll come to that shortly. Another thing that I mentioned while showing you the slides in my previous video is that I want the height of this cell to be roughly around 1.6 micron. So let's use the ruler by hitting K and measure out 1.6 micron. There seems to be some issue, excuse me for a while. Let me just okay, let's resume now. So hit K and measure out around 1.6 micron, so that's somewhere roughly around here. Okay, just leave it there. I'll copy this metal line because I want one metal line for the ground, so hit C, click on that line, copy paste it here. You see that by ensuring that it only moves in one direction, these lines are automatically perfectly aligned, which is something that's that can be very important. Okay, let's move this back up a little bit. I think I moved it a bit too much. Let's move the PMOS device slightly up, the NMOS slightly up. Okay, now let's start making the connections. The first connection I need to make is to short the gate of the two transistors. If you see the schematic, the gate of the two transistors are shorted and given the input is given there. So let's do that in the layout. Let's come here, zoom to the relevant area. You see that the gate is where, sorry, let me zoom back. Gate is where the polysilicon crosses the diffusion layer. So this blue region here is the gate of the PMOS transistor, and this blue region here is the gate of the NMOS transistor. Let's connect the two gates. To do that, I need to draw a rectangle in polysilicon. Polysilicon is actually called PO1. That's something you need to remember. So let's select that in the palette here, and now draw a rectangle by hitting R, and then completing. You see that as I'm about to draw this rectangle, the tool automatically highlights it in using the white borders. This actually greatly helps you in doing layout. It is pre-anticipating what needs to be done, and it's trying to guide you in doing the layout process. So let's hit fit screen again, and let's save our design. It's important to keep saving because these tools are complicated, and they are bound to have some crashes in between. So it's a good idea to keep saving. We have to short the drain of the two devices. We'll do that in metal 1. You see that you see that the diffusion regions shown in red have been brought up to metal 1. So the diffusion to metal 1 via or the connection is already present in the transistor. So all we need to do is to connect the two drains is to short this terminal here with this terminal here. Let's first select metal 1. By hitting R, let me hit R and zoom to this and hit R now. Now I zoom out by hitting Shift Z. So do that. Zoom again to ensure that I have perfect alignment with this, and click. So now I have these two connected. You see that it automatically highlighted them for a second, showing that they are connected. I need to connect the source of the PMOS transistor to the supply rail. Let me do that again. I hit R for the rectangle, start point, and let me align this correctly to the supply rail. Right, so supposing I draw a rectangle that is much bigger than I intend it to be, and I want to scale it. I don't want to redraw the entire rectangle. So you can do that by hitting the letter S. So hit S, you see that only that edge highlights, not the remaining edges. However, if you hit M or C, the entire thing highlights. So let me show that to you. If I hit C and move my mouse pointer in between, you see that the entire block highlights. The light yellow border comes across on the entire block. However, if I hit escape now to undo that command, deselect that move command and then hit S, you see only that particular edge highlights. When this happens, I can click there and then scale that. So that can be used to resize rectangular blocks. So let me select that and hit delete so that that thing goes away. Let me short the source of the NMOS device to the ground. So I hit R. ME1 is selected for metal 1, so I don't have to worry about that. Let me zoom so that I get my edges aligned, so it makes for a neat layout. So that is done. Now I need to bring the poly layer up to metal 1 layer. Generally, almost routing between blocks that are far away is done using metals. The obvious reason is that because it has lower resistance, it gives better performance. So let's bring out the poly, the gates of the two devices that are connected using poly to metal 1. The way to do that is by creating a via. The command to do a via, the command to instantiate a via is O. Hit O to bring up this dialog and select in this menu, select the via that you want. So we want a connection via between metal 1 and poly. So select that metal 1 underscore M1 underscore poly. Say that you want two contacts, you're putting an additional one just for redundancy or for reducing the resistance of the contact. So you want one row and say two columns. Say hide and place this. Let's place this. And I need to connect both of them. So let me create a rectangle by hitting R and create a rectangle between this and this. Oops. I created a rectangle in metal 1 by mistake. What I meant to do is create a rectangle using poly. So all I can do is that just like in schematic, hit Q and select that. So you can edit the triangle properties, tell it that it's currently in ME1 layer, you want it in poly, so scroll down to poly, that's PO1, and say OK. So that is now in poly. So let's zoom out to see our design. Now we need to tell the schematic which what each terminal is, and the way to do that is by labeling nets, just like we did in schematic. So hit L. This is the same thing that we used in a schematic editor. Let's label this VDDI. The font, let's make it Roman so it stands out clearly. Then let's choose the height of that to be around 0.1 microns and hit hide, and then place it on the Y that you're interested in. One thing to note here is that by placing this, I forgot to tell you something there, so let me delete that and redo that. So the way to put label is by selecting L, write the label name here. You need to select on what layer it comes. This is important. It's important that you select a text layer, not the drawing layer. So let's scroll down, see all the DRW layers stand for drawing layers. We want a text layer, so we need to scroll down until we get text layer. Let me try and speed this up. Okay, so the text layers are here, TEX, and this, since this is metal one, I have to choose this M1 cat TT. Sorry, M1 cat TEX text. It's very important that you choose the correct ones here. Click hide and then place it here. When you place it here, it's important there's a small plus symbol at the right in the center of text. Ensure that that aligns with this metal one rectangle in the background. If I do this, if I place something like this, then the plus symbol that is present here is not aligned or not placed on this metal, which means that the tool does not understand that I am labeling this net represented by this rectangular block as VDI. So to ensure that the tool understands it, move it so that the plus symbol is present on that. So, okay, so let me copy this and then paste it here so that I can create the ground net or label the ground net. So similarly, I hit Q, change the name GNDI, hit OK. Similarly, I need to create the input, so let me copy this, move it. See, I can't move it straight away here, I need to first move it here, then again hit M, move it there. What I want to label that move slightly up. Okay, hit Q, change the label on that to input or IN. Okay, so the plus symbol is aligning on that, so that is all right. Now let's we are not labeled the output net, so let's copy this, paste it here, select this, hit Q, change into OUT out, hit OK, and that should be done. So we have had the input and output, we have supply and ground. Now let's go ahead and see if the DRC passes on this. So DRCs are basically rules that govern the design of layout of the design of layouts. These are given to us by the foundry to ensure manufacturability of the design. So rules are saying, for example, that two metal one lines cannot be closer than some limit that it imposes, or a metal one line cannot be thinner than some limit that the foundry imposes. A full list of all the design rules is present in the document whose link is given here. Okay, this is a fairly large document, so when you have some time, it's a good idea to skim through this to understand all the design rules. Other rules are present here, so when you have some time, go through the documentation to the link of which is given on the website that I showed earlier. So let's get back to the layout and see if all the design rules are met in our layout. The way to do that is we use a tool from a company called Menta Graphics called Calibre. So click on Calibre, say that you want to run DRC. Once that thing opens, so a window should open and it will ask you for run set file. Okay, so what I'll do is browse here, go to my work CAD, it's already done here, so and select this DRC underscore 65 nanometer underscore run set, so hit OK. When you open that run set, what happens, because you copied it from somewhere else, some of the paths are not correct. So it asks if you want to create a path in home smart. That's not where you want to create it if you're not the username called smart. So I'll hit no, go to the rules file, rules tab here, and then correct this path. So I'll use the browser here. The username that I'm using on this virtual box is called Viveka, VIVK. We'll type down the path there. In that I go to work CAD. There I have a directory called select that directory, hit OK. So I want all my log files here. One thing worth remembering is that running DRC, LVS and PEX that we'll be shortly doing generates a lot of files, a lot of log files and a lot of other garbage files that you don't want to be present in your work CAD directory. It simply messes things up. So let's it's better to create a separate directory for this and store all the log files there. Okay, so once all these things turn green, you're ready to run DRC. So click on run DRC. It says, do you want to overwrite some layout files? Say okay. It says, do you want to save your layout? Obviously you want to save your layout. I forgot to do that. So now the DRC is running. Should be, because this design is fairly small, DRC should run pretty quickly. So let's see. So it generated a report Okay, there's some spurious error here. This is some kind of demo effect. Hopefully you will not see this error. I think it should be simply resolved by rerunning it. So let's try and rerun it now. Running. So the report got generated, and this is the result of the DRC run. It says there are 1, 2, 3, 4, 5. There are 1, 2, 3, 4, 5 violations of DRCs. So let's go see what they are. So let's select the first one is selected now. It says the minimum spacing and notch of PO1 on filled is 0.12 micron. So if you double click on this error, it says there are two errors, see, 1 and 2. If you double click, it zooms to the area where the error exists. So let's go back to the layout editor. Let's see. So the yellow highlight here shows that this way there's an error. See, there's a tiny notch. Things like this are not allowed as per DRC rules. Now if you go back to the DRC window, where was the DRC window, and double click on 2, it shows where the second error is. So let's fix this error. A simple way to fix this error is to move this polysilicon layer here, use S, scale the size of this so it aligns here. So now there's no notch there. Let's save this. Let's go to DRC and run DRC again. So last time you saw there were 5 errors. Hopefully that will be reduced to 4 this time. So that error got fixed. There are now 4 errors. Let's not bother about this error. Let's go to the second error. So here the error is that the error reads maximum n plus diffusion to nearest p plus pickup spacing is 30 micrometer. What we forgot to do in the layout, let's go back to the layout here. I'll hit F to fit screen. We have not created a substrate contact for PMOS and NMOS transistor. Of course, if you don't have sufficient number of substrate contacts, the danger is that there might be latch up. So that is the warning it shows there. So let's add substrate contact for the PMOS and NMOS transistor. For a PMOS transistor, remember that it sits in an N-well. So we need to create a contact from the N-well and connect it to the supply rail. So to do that, hit O, the same thing that you used to place vias, and select that you want to create M1 to N-well contact. Okay. Let's hit hide and then place it. Now since I'm already used to making layouts, I know that it will give a DRC violation if I leave any space between two N-wells. If I leave too little space, so I've carefully placed it so that there's no gap there. Okay. Now let's connect it to the supply rail. I select ME1 here, it's already selected. Now I hit R to create a rectangle, so that this is now connected to the supply rail. So that is done. Now we need to connect a tap substrate contact for the NMOS device as well. Of course, now we need to connect a P plus region. So hit O again, select M1 to P active or P sub, either will do. Hit hide. Now place this carefully. I know how closely I can place this, so I'll place it right there. Okay, you'll get used to these rules as in when you start doing more and more layouts. I'll create a rectangle again to short this to the supply rail. Okay, and then save this layout. Let's now go ahead and rerun DRC. So we had 4 errors last time, if you remember. Now let's see how many errors remain. So DRC ran fairly quickly here. Now see, only 2 errors remain. Both of these errors can actually be waived off because they are related to density rules, and they apply when you do a layout at chip level, not at block level. It says the density of some material is low, so don't worry about these two. So remember, these two are the errors. You'll quickly get used to them, that are waived. So you can say is okay, so our design is now considered DRC clean. So let's exit this. It asks, do you want to save changes to run set? If you make any changes, you can save it. I'm not interested in saving changes, so I'm going to select no. Okay, once DRC is done, we need to ensure that whatever layout we created is actually same as the schematic that we created. So let me go to the layout editor and hit F. Okay. So the rulers that we created can be removed by hitting Shift K. That's something I did not tell you earlier. So if you hit K, it brings up the ruler and you can measure stuff. You can have lots of measurements, and that can be that can get really ugly really quickly. So to remove all of them, you can hit Shift K and all of them disappear. Another thing that I did not show you, lets me hit F to fit screen, is that the ruler sometimes has this snap to edge thing enabled. If you do this, you see that as soon as I go close to an edge, it sort of sticks to an edge. This can be annoying, so you can right click while ruler is selected and then unselect that, so that your mouse or the ruler can move around freely. Now once a DRC rule check is done, next thing is to do what is known as LVS check. LVS stands for layout versus schematic. What I'm trying to do here is to ensure that the connections that I made in layout are exactly the connections that I intended to make in schematic. So I'm doing a check between my layout and schematic to check if both are the same, they are equivalent. So go to Calibre, again we use the Calibre tool to do this. Calibre tool to do this, go to Calibre, hit select run LVS. Again it asks you to select an LVS file. Since I've already done this in the past, it is selected. Let me browse it. Let me browse and select it just to show you how it's done. So browse, so it comes up by default in your work@. directory. Go into this folder called runsets, which you have copied earlier. Select LVS, runset, hit OK. Hit OK. Now if everything, now again the same similar issue with the run directory. So would you like to create it so it asked, do you want to create a work directory in Smart? No, that's not something we want to do, so I'll select no. Go to rules again, browse and ensure that I select the directory that I actually want to put all my logs in. So I select that, sorry, last thing only has to be select that, not double click it, and hit OK, so that gets selected. Inputs, everything seems to be selected. Okay. Another thing that you need to select here is to ensure that it asks where do you get layout, where do you get the netlist. What the tool actually does is a comparison between the netlist that it will extract from the layout and the previously existing netlist. So it asks that what is the netlist of where do you want to get the netlist from. So go ahead and select the netlist tab here and then select export from schematic viewer. You're telling the tool that extract the one netlist from the schematic, extract the second netlist from the layout, and compare that these two netlists are actually the same. Okay, let's go ahead and ask it to run LVS. Give something, say okay. It says, do you want to save your layout? I seem to have forgotten to do it, so let me select yes. Okay, now we'll wait for the layout editor LVS checker to run. If everything goes okay, we should see a big smiley confirming that our layout and schematic match each other. This is actually trivial because our design is so small right now, but when designs become big, you see that this is not this is not a simple thing to do, and it might take some significant effort for you to get make your design LVS clean. So once you see the smiley, you can close this guy. Your LVS task is done. Again, when you close it, it asks you if you want to save your runset. Say that you don't want to do it. If you want to save it, select yes and choose the appropriate file name. Again, next step is of course to run it PEX. PEX stands for parasitic extraction. So once you have a layout has additional information than schematic. How have you placed the transistors? How much metal line have you used? How wide are these metal lines? Right? If the metal lines are wider, you have low resistance. If you have small, thin metal lines, they have higher resistance. So all this information is necessary to extract parasitic information. These are parasitics, right, to the transistors. So we are going to extract these parasitics from layout and annotate it back onto the schematic, and this will enable us to run more accurate simulation and get more accurate results that more closely match the results we are the results that we expect to see once the chip comes back from the foundry after being manufactured. Again, this also asks for runset file, so let's browse, select the runsets directory, in that select the PEX runset, select OK. Again, you see the same issue with the directory where you want to place your logs. Say no. I'll go to rules again, browse so that I get to where I want to be, select my work@. directory, save the directory, hit OK. So that is done. Once all these are green, see that rules, inputs, output and run control are green, you can say run PEX. Says you want to overwrite for some file, say OK, say OK. Now this should bring up a big dialog box which says that how would you want so it extracts a schematic from this layout. So it asks in this particular dialog how do you want that schematic to be created. So it's first of all these three options you need to remember. So it's select schematic in the type of view you want, ask it to create all terminals for it, and then ask it to place these things in an arrayed fashion. These are not compulsory, but you see that these are convenient options to have. So then select OK. So 3 options on that, remember. Once that is done, if everything goes well, you should get 0 warnings and 0 errors. So you'll close this. Our work here is also done, and let's exit. It's again asked, do you want to save changes? If you want to save, go ahead and save. If you don't want to save, say no, and you're done. So we have created the layout, done DRC, done LVS, and then done PEX. We'll see how to use this parasitically extracted information in our next video. Before that, let's go back to the library manager and see this new view that is created for you. The view is called Calibre view. So double click on this. You see that schematic editor opens and schematic is created for you. The elements are so small that they are not easy to see when it's completely zoomed out. So let me zoom in. On top are the IO ports of the design, 4 of them, same as the schematic you created. The 2 transistors, so they are placed here. All the parasitics are placed here, so there are lots of capacitances and tiny resistances. So in the next video we'll see how these affect the performance that you can measure using simulations. So I'll stop this video now. See you in the next video.